Welcome to the visit training session titled Basic Satellite Interpretation in the Tropics. My name is Dan Bicus. This training session is based on a NESDIS workbook produced in the mid-1990s titled Tropical Clouds and Cloud Systems Observed in Satellite Imagery by Vern Dvorak and Frank Smigelski. The workbook consists of still black and white images, so the objective here is to revisit some of these training topics with animations of color-enhanced satellite imagery. For our learning objectives, we will be looking primarily at GOES visible, IR, and water vapor imagery to address the following objectives: tropical cloud identification, mesoscale vortices, such as mesoscale convective vortices, various differential heating effects, such as the sea breeze, island effects, easterly waves, surge lines, ITZZ flare-up, and note that tropical cyclones will not be addressed during this training session. There are numerous other training sessions devoted to this important topic. We'll begin with tropical cloud identification with visible satellite imagery. There are two major categories of clouds in the tropics: Cumuliform and Stratiform. The two major types of Cumuliform clouds include Cumulus and Cumulonimbus. Cumulus appear circular or globular with sharp edges, and they're usually arranged in lines or cellular patterns. Cumulonimbus are circular or oval with distinct edges and a cirrus plume. They're rounded clouds with a cirrus canopy. They exist as individual cells, clusters, or lines. Their associated cirrus anvil may cast a shadow, and this can be a distinction when looking at them in the visible imagery. And they're also brighter in terms of their appearance compared to the cumulus clouds. This is an example of cumulus lines or streets near Jamaica. I'll go ahead and circle these here, the region of interest. Small cumulus are limited in vertical extent by an inversion and become arranged in streets along the wind. These are wind-parallel cloud streets that rarely produce precipitation, except when cumulus lines merge. Moving further west, we see examples of cellular cumulus lines. These are circular or globular with sharp edges. Rainfall-producing clouds are associated with shallow cumulus clusters aligned in arc-shaped formations, as well as the cumulonimbus. The cumulonimbus are brighter and have a distinct edge on the upshear side and a cirrus plume in the opposite direction on the downshear side. In this example, we see a number of different cloud types. South of Cuba, over here, we see a series of long cumulus lines. Localized cumulonimbus is found in convergent regions. Over much of the Gulf of Mexico, we observe cellular cumulus lines that are circular or globular. Cumulonimbus develops in the various convergent regions. Over the Yucatan Peninsula, we see wind-parallel cloud streets and localized cumulonimbus development. Also note the different anvil orientations from convection across various parts of the seam. This can be useful information to get a quick look at the mid to upper level flow across the region. Here we analyze lines of cumulus that appear similar in the visible imagery, but we need to distinguish between the different lines of cumulus observed. First, I'm going to stop the loop and note these lines of cumulus south of Jamaica right here. These are pretty much what we've been talking about in the previous slides. Now I'm going to advance the loop some, and we see just north of this region of convection, which is located right here, we see various lines developing, and I'll show those at different times here. Here are those lines. Although these lines appear similar to the cumulus we've been discussing, this is not the same feature. This is an arc line, which is also known as an outflow boundary or gust front. Outflow forms as the thunderstorm begins to dissipate. The further the outflow boundary is from the parent thunderstorm, the weaker the winds become. The winds can be significant just along and behind the arc line. Here are the characteristics of arc lines compared to cumulus lines so that you may readily distinguish between the two when viewing visible imagery. While arc lines are a product of thunderstorm downdrafts, cellular cumulus lines are formed by changes in the wind speed and horizontal shear in the general wind flow. They are a product of mesoscale convective mixing within the large-scale flow. Arc lines are found over relatively small areas, whereas cumulus lines are found over vast areas. Arc lines exist for a few hours, whereas cumulus lines can exist for days. Arc lines may initiate thunderstorms, whereas cumulus lines rarely produce precipitation, the exception being merging cumulus lines. This loop contains visible imagery during the day and 3.9 micron imagery at night. The motivation here is continuity so that features can be followed along and help discriminate between cumulus lines and arc lines. Note the cumulus line northeast of Puerto Rico has the characteristics described in the previous slide, including its existence over a large area spanning a long time period. Near the end of the loop, we observe an arc line associated with outflow from thunderstorms west of the Antilles. I'll go ahead and stop the loop and highlight that. Here's the convection of interest right here, and then we see an arc line emanate out towards the west, on the west side of the convection right here. Now let's discuss the other major cloud type we see in the tropics, and that's stratiform clouds. These can be broken down into two categories. First, stratus clouds, which are uniform gray layer with smooth tops, and stratocumulus. These are globular-shaped elements within a stratiform region, closed cellular patterns over the oceans, and also have bright centers with gray at the edges. Off the west coast of continents, they may merge or become cumulus further from the continent where the inversion is higher, and stratus or fog closer to the continent where the inversion is lower. Note that this is true off the west coast of continents where subsidence associated with the subtropical high exist. Examples highlighted here are off the west coast of North America. Both of these cloud types may be distinguished from higher clouds of equal brightness by their sharp edges when encountering higher terrain. This is an example showing widespread stratocumulus across the Gulf of Mexico behind a strong cold front. These can best be described as globular elements in line patterns parallel to the low-level flow. The line patterns would indicate instability, as we'd expect with a relatively cold air mass flowing over a relatively warm water surface. Note the bright centers with gray, or less bright, near the edges due to change in cloud depth. And that can be highlighted pretty well right here. Over Mexico, we observe stratus clouds, which appear smoother and more uniform in appearance than stratocumulus. The stratus has a sharp edge at the edge of the higher terrain. This can be useful when there are nearby higher clouds around of comparable brightness in order to distinguish cloud type. Here's an example of stratocumulus with closed cellular pattern over the ocean, northeast of Hawaii in this case. The large globular shapes indicate a stable air mass, as we'd expect with relatively warm air over a relatively cold water surface. Larger cell size is generally associated with a lower inversion. Note in this scene, as we move from east to west, there is a transition from stratocumulus to cumulus clouds in the vicinity of Hawaii. As the distance from the west coast of a continent increases, the height of the inversion increases, allowing for the transition to cumulus clouds. Note the cirrus over here that moves over Hawaii. It's quite subtle in the visible imagery. However, we know it's cirrus since it's moving in a different direction than the low-level clouds. Let's compare the cloud types we've discussed already in the visible imagery to how they appear in the IR and water vapor channels. Our motivation here is to distinguish low-level or warmer clouds versus high-level or colder clouds. Low-level clouds do not appear in water vapor imagery. That's important to keep in mind. And also, we want to compare cumulonimbus in visible, IR, and water vapor imagery. Here's the example we showed 2 slides back with the stratocumulus to cumulus transition near Hawaii. only now we're looking at the IR imagery. There is much less detail here. The cloud top temperatures are relatively warm. The transition from stratocumulus to cumulus is almost too subtle to be detected. Late in the loop, we see cirrus clouds moving in over Hawaii. These are much colder cloud tops, therefore they do show up well in the IR channel. Recall in the visible loop that the cirrus clouds over here were more difficult to detect. Here's the water vapor imagery over a slightly larger scene northeast of Hawaii at the same time. The low-level clouds, the stratocumulus or the cumulus, cannot be detected. Remember not to use water vapor imagery when analyzing low-level clouds. Tropical storm Chris in the visible imagery shows bright cloud tops where cumulonimbus is present. During midday hours, the viewing angle makes the cumulonimbus appear very bright, making it difficult to detect details that are apparent earlier or later in the day. This is the visible loop the day after the previous slide. Now Tropical Storm Chris is just a remnant low. Most of the cumulonimbus is no longer present. The storm weakened during the overnight hours, so we'll look at the IR imagery next. This is the IR imagery for the previous 2 days, including the nighttime imagery. I'll change the enhancement from a linear grayscale to one that includes colors. Note how much better the cold cloud tops stand out when enhanced with a color table. There are 2 advantages to the IR imagery in this example. The first is continuity. We can now see the transition of Tropical Storm Chris to a remnant low due to the loss of convection. The continuity through the night allows us to see when the convection decays. The other advantage is greater detail in the cumulonimbus tops. This is particularly important at night or when the sun angle makes for very bright or highly reflective tops in the visible imagery. The IR imagery does not experience this effect. Here, we will step through a visible, IR, and water vapor image at the same time to make comparisons between the different channels. Consider these cumulus lines east of the Antilles in the visible imagery. They show up clearly since they're reflective. We switch to the IR imagery, and we see that they're much more subtle. The brightness temperature associated with the cumulus lines are relatively warm. Since these are low-level clouds, this makes it more difficult to detect in the IR than in the visible imagery. And if we switch to the water vapor imagery, as we'd expect, these cumulus lines are undetectable. Now let's switch to the cumulonimbus west of the Antilles, looking right here. The IR imagery will generally show cumulonimbus as larger than the visible imagery. Go back and forth between the two, and you can see they appear larger compared to the visible imagery. This is due to the resolution of the sensor and the cold cirrus temperatures. Now let's look at the thicker cirrus down here. In the visible imagery, essentially the anvil blow-off from the cumulonimbus to the north here. The thicker cirrus south of this region of convection is easy to identify since it's reflective. However, notice the region of thinner cirrus around Hispaniola up here. In the visible imagery, this is more subtle, less reflective, compared to the IR imagery. The cirrus stands out more due to the cold cloud top temperatures. In the water vapor imagery, the cirrus still stands out, but not quite as well as in the IR due to the background. The IR background is the surface, which is warmer, while the water vapor imagery is much higher up, therefore colder, so that the cirrus is observed on a colder background in the water vapor imagery compared to the IR imagery. Note the east to west oriented cirrus south of Puerto Rico right here. As we go from the visible imagery to the IR imagery to the water vapor imagery, it appears to cover a larger area. This is because in the IR and the water vapor images, the cirrus appears brighter and more dense because of the colder cloud top temperature and the lower resolution of the IR channel being 4 km versus that of the visible, which is 1 km. This spreads the brighter region over a larger area, thus the cirrus appears to cover a larger area. Let's look at diurnal trends over tropical oceans. Thunderstorms associated with cloud clusters, MCSs, tend to peak during the early morning hours with dissipation during the afternoon. Cloud line boundaries do not follow the same diurnal pattern. Keep in mind that over land, convection tends to be diurnal, particularly over higher terrain. In this loop, we see a cluster of thunderstorms south of Cuba in the morning. Note the extensive cirrus in the earliest image associated with a peak in convection during the early morning hours. As the day progresses, the convection associated with the cluster decays. Meanwhile, cumulonimbus develops along the sea breeze boundary over Cuba and along cellular cumulus lines further south over the ocean. Mesoscale convective vortices are important in the tropics because they can spawn new convection. Conditions favorable for MCVs, such as low vertical shear and high low-level moisture, are common in the tropics. MCS can spawn an MCV overnight, and studies have shown that 60% of MCVs force new convection. If you want additional information about MCVs, there's an entire visit training session devoted to that tropic that you can find here. In this visible loop, we see an MCV over Florida moving eastward. By late in the day, we see new convection associated with the MCV. Just looking at the visible imagery alone, it's unclear what the origin of this MCV was. Next, we'll look at IR imagery to go further back in time during the overnight hours to determine its origin. Here's the IR imagery for the day before the previous slide, through the overnight hours and through the daytime. The initial convection appears to be associated with a sea breeze. As we look in this area right here, we can see convection associated with a sea breeze developing. And then we see upscale growth into an MCS during the overnight hours, and that led to the development of the MCV that we see across Florida. The MCS spawns the MCV that we saw more clearly in the visible imagery in the previous slide. At times, there are signatures in the visible satellite imagery that can indicate whether a sea breeze will develop or not. When we observe cumuliform organized into lines oriented perpendicular to the coast, sea breeze development is unlikely. This corresponds to onshore flow greater than about 10 knots. If no line pattern exists in the visible imagery, then you need to assess the possibility of a sea breeze developing, including onshore flow less than 10 knots, then assessing the land-water temperature difference, the cloud cover, and so forth. Here we observe cumuliform organized into lines oriented perpendicular to the coast across Texas and also across Louisiana. This indicates relatively strong onshore flow. Observations show that onshore wind speeds are mostly above 10 knots. In this situation, the pressure gradient will override the effects of differential heating, and the sea breeze front will not develop. Note in this example, although there is no sea breeze front for convection to develop along, there are other boundaries, such as cold front and outflow boundaries, where convection is developing. We move further east at the same time depicted in the previous slide. Here we did not observe cumulus lines along the shoreline. At this point, we can evaluate the potential for sea breeze development. An overlay of the surface observations shows light onshore flow and warming temperatures, including not that much cloud cover early in the day, allowing for warming to occur, favorable for sea breeze development. And sure enough, we see the sea breeze develop over a fairly large segment of the coastline here. Islands have a profound effect on cloudiness. They can also affect the low-level wind flow by distorting the flow into eddies and streets around and over the island. In this example over Hawaii, we see blocking effects and easterly flow. Note the cloud streak caused by deflection of the flow around the islands. These streets are associated with locally stronger winds. Note the downslope and upslope regions on the Big Island of Hawaii here around the mountains. This has significant effects on precipitation. An easterly wave is defined as a speed maximum in the low-level easterlies with cyclonic vorticity concentrated on the equatorward side of the speed maximum. Identification of easterly waves is important because they may bring rainfall, strong winds, and even initiate tropical cyclones. The weather associated with easterly waves varies depending on such factors as sea surface temperature and upper air environment. There are, on average, 80 easterly waves per season between the spring and the fall in the Atlantic basin. Satellite imagery is critical to identification of easterly waves since they exist mostly over data-void oceanic regions. The wave exists along an inverted trough, such as is depicted right here, with surface divergence ahead of or west of the wave, and surface convergence, as is shaded right here, behind or east of the wave. This is typical in the western Atlantic. However, this divergence-convergence pattern varies. For example, over the West Pacific and on occasion in the Atlantic basin near the African coast, the opposite occurs. The greatest amplitude is usually between 850 to 700 millibars. The surface wind direction changes from northeast to southeast with the passage of a wave. In satellite imagery, there are two types of easterly waves that distinguish their appearance. The first is the curved cloud band, and the second is the inverted V. This is an example of a curved cloud band easterly wave in the visible imagery. The leading deformation zone is in advance of the speed maximum, which is right here, in the low-level easterly flow and is generally oriented perpendicular to the speed maximum. The trailing deformation zone is at the rear of the speed maximum in the easterlies and is generally parallel to it. Streamlines typically cross these deformation zones in a diffluent pattern. The wind speeds usually decrease significantly in the diffluent pattern across the band. Deep convective clouds exist near the equatorward end of the trailing band, should be right around here, and also near the area of maximum cyclonic rotation, which you can see near the end of this loop right here. This is the same time period as the previous loop, except here we're looking at the IR imagery. The advantages are that the deeper convection stands out more readily and we have continuity through the nighttime hours. The disadvantage is that the low-level clouds are more subtle, making identification of the wave somewhat more difficult than visible imagery analysis. This is also the same time period as the previous loop, except here we're looking at the water vapor imagery. All low-level cloudiness is undetectable on this channel. The only evidence of the wave is indirect, that is, the convection that exists as a result of the wave. The value added by the water vapor imagery here is an analysis of the upper air environment, which gives a better understanding of the weather associated with the wave and potential for tropical cyclogenesis. In this example, we see subsidence ahead of the wave and deeper moisture and upward motion east of the wave axis. This is a longer loop of the easterly wave in the IR channel. The long loop has the advantage of continuity. Notice the persistent convection where the trailing band intersects the ITZZ. I'll go ahead and stop that. Right around here. This is where the convection from the trailing band intersects the ITZZ. A wave-shaped pattern of deep convective clouds exists along the ITZZ south of the easterly wave at this time. The ITZZ perturbation and easterly wave usually move at different speeds, and as you can see here, the easterly wave is moving faster towards the west, and that leaves behind the ITZZ perturbation, where eventually we see the convection decay here, and this wave continues on towards the west. We're we're still looking at the same easterly wave, this time as it's approaching the Lesser Antilles. We've overlaid the GFS MSLP in cyan and 650 millibar streamlines in red with the IR imagery. The wave is coincident with the inverted trough in the MSLP pattern, and convection exists on the convergent or east side of the wave axis. Also, the 650 millibar streamlines lags further to the east. Here's the inverted trough associated with the 650 millibar streamlines, which is what we'd expect. Keep in mind, since we're typically in regions with limited data, these patterns may or may not show up in the model output. If model output does agree with conceptual models of what you observe on satellite imagery, this should give you more confidence in your analysis of the wave. The pressure field can give you an idea of the magnitude of the easterly wave. The other type of easterly wave we typically see in satellite imagery is the inverted V. This is basically the curved cloud band wave without the leading deformation zone. Deep convective clouds are present along the ITZZ to the southeast of the wave. Note the area of dust east of the wave. This usually coincides with a mid-level wind maximum. Here we're looking at the IR imagery of the easterly wave from the previous slide. The low-level cumulus are more subtle than in the visible imagery. However, the cumulonimbus induced by the wave show up more clearly with the colder cloud top temperatures. Continuity is also an advantage here. Here's an analysis of the wave from the previous slide, and you can see the inverted phi signature present right here. MSLP from the GFS is in cyan, and 60-50 millibar streamlines are in red. The wave is coincident with the inverted trough in the MSLP right here, and we also see the inverted trough in the 650 millibar streamlines lagging just to the east, which is what we'd expect. And also, just as before, keep in mind, since we're typically in regions with limited data, these patterns may or may not show up in the model output. If the model output does agree with conceptual models of what you observe in the satellite imagery, this should give you more confidence in your analysis of the wave. Tropical waves are analyzed in the surface analyses done by TAF-B. Note the winds veer in time over the Lesser Antilles with the passage of the wave of interest, going from easterly before the wave and then turning over to southeasterly here after the passage of the wave. This is the NESDIS blended total precipitable water product over the Atlantic. The TPW product is a good tool for tracking easterly waves, since there is a maximum in TPW along and east of the wave due to convergence and advection. In this example, we see a maximum in TPW moving just off the coast of South America in this direction, and that is the wave we've been analyzing as it moves through the Lesser Antilles. Let's look at another example of an easterly wave. This is from August 2009. This wave has some characteristics of both the curved cloud band and the inverted V. The leading deformation zone is present early in the loop, but seems to be decaying in time. The inverted V signature can be seen fairly easily when you focus on the low-level cumulus, which is approximately right in here. There is more convection associated with this wave than the previous examples, so this wave appears to be associated with considerable shower and thunderstorm activity. This is the water vapor imagery of the easterly wave we were looking at from the previous slide. The water vapor imagery will only be able to detect the upper portions of an easterly wave. At times it may show up, but it cannot be counted on to reliably track easterly waves. TPW has a large advantage over water vapor imagery in that it detects water vapor at low levels where the wave exists, so it will be a reliable tool to track waves. Here's the GOES total precipitable water product. The easterly wave can be tracked as a maximum in the TPW. The maximum associated with a wave can clearly be tracked as it's moving across the Atlantic and moving towards the Lesser Antilles. The advantage of this product is continuity, in that the wave may be tracked for multiple days back to its origin. The nature of the displayed data, that is, loops over multiple days, helps keep track of the wave for longer periods of time. Another useful tool for tracking easterly waves is the WaveTrack product from SIMS. In this example, the GOES visible or IR image is overlaid with the GOES cloud drift low-level winds. Only winds in between 600 and 925 millibars are shown for this product. You can identify the wave east of the Lesser Antilles, at this time right here, that we had been looking at in the visible imagery, and then we can track this along here as it's moving towards the west. The winds are northeast or east ahead of or west of the wave, and southeast behind or east of the wave. The advantage of this product is that we can look at many wind observations over a region where surface and upper air data is sparse. This is another product that's available from SIMS called the 850 millibar vorticity tracker. This product depicts the low-level 850 millibar vorticity that is often associated with tropical waves, tropical cyclones, and synoptic scale features. No-GAP's model data is used as first-guess background field to stabilize each analysis. Satellite-derived cloud drift winds are then applied to this field, utilizing a recursive filtering technique. This technique allows for the satellite data to dominate the relative vorticity analysis. The easterly wave of interest shows up as a maximum approaching the Lesser Antilles. Surge lines, also known as convergence lines, are important to distinguish from some of the other types of lines we've been discussing. They're long arcing lines of cumulus and cumulus congestus, likely associated with an easterly wave. The leading edges denote convergent low-level winds. They may lead to showers and thunderstorms, along with temporary strengthening of surface winds. And thunderstorms tend to develop during the daylight hours, particularly during the afternoon. Next, we'll look at an example of a surge line. Here's a combination of visible and 3.9 micron imagery at night with a linear black and white enhancement. Note the surge line east of the Lesser Antilles. The cumulonimbus is primarily at the northern end, interacting with the vorticity center, and at the southern end, interacting with the ITCZ. At nighttime, in the IR imagery, the low-level clouds are more subtle. However, the advantages are that we have better continuity. Keep in mind, although the cloud top temperatures are relatively warm, therefore subtle in the IR imagery, the rainfall may be heavy in places due to warm rain processes occurring. Here's another example of a surge line in the visible imagery. Note how far north-south the line is. The convection is enhanced over the portion of the line that is over Cuba, perhaps due to sea breeze convergence interacting with convergence from the surge line. The last topic we'll discuss are ITZZ flare-ups. An ITZZ flare-up is a rapid poleward expansion of mid and high-level clouds in advance of amplifying troughs. ITZZ flare-ups are also known as Pacific moisture conveyor belt or a warm conveyor belt associated with cyclogenesis. They're characterized by a jet stream max on the western side of the trough. They're prevalent during winter but can occur during the warm season. The occurrence of precipitation under the flare-up varies depending on the vertical depth of the jet stream, and they may introduce cloud cover for potential severe weather events in the southern U.S. Other forecasting applications include forecasting sky cover and temperature. Satellite imagery is key for analyzing ITZZ flare-ups since they occur over data-sparse regions and develop rapidly, so that the models may struggle to pick up on them in a timely manner. Although we can view this in visible imagery, it's best to analyze flare-up events with IR or water vapor imagery because we need that continuity. It's very important. And also, cirrus shows up better in the IR water vapor channels versus the visible imagery. In this example, we see the development of high and mid-level clouds in this region here, northeast and east of Hawaii. And they rapidly move in this direction towards the southern U.S. In the typically strong upper-level winds during the cold season, it doesn't take long for this cloud cover to advect to the southwest U.S. over here, as shown. Generally, when the cloud structure appears relatively even, as opposed to irregular in the IR imagery, the clouds are deeper and extend to lower levels of the atmosphere. And what I might mean by that, I'll need to stop the loop here and go to a particular time. Irregular means we see imagery characterized by something like this here. In other words, we see a lot of space in between the colder cloud top temperatures. This would be characterized as an irregular structure in the appearance of the clouds in the IR imagery. And then a little bit later on, in this region right here, this would be referred to as an even appearance in the IR imagery. And this is when the clouds are deeper and extend to lower levels of the atmosphere. Precipitation is more likely when the cloud structure is more even compared to the irregular structure, such as what we saw earlier in this image. Here's the water vapor imagery for the same time, and the advantage here is you can get a good idea of where that trough is, and you can see this trough digging towards subtropical latitudes, and then we see the development of the ITZZ flare-up in this region moving towards the southwest U.S. Here's a different ITZZ flare-up event in the water vapor imagery, and I'll overlay the 250 millibar heights here as well. What we're going to do is look at the sequence of signatures to look for in the water vapor imagery for these ITZZ flare-up events. So the first signature you would look for is right here off the coast of California. We see an upper level trough at subtropical latitudes that's amplifying. The next thing we would look for are these cirrus and mid-level clouds that spread poleward from the ITZZ, and a well-defined cloud boundary forms on the poleward side. And that's best shown in this example right here. This is that well-defined cloud boundary that forms on the poleward side of the flare-up. Next thing we would look for are on the cloud boundary here, and the cloud boundary and the jet stream on the forward side of the trough become oriented more in the north-south direction. I'll go ahead and depict that here. Notice how we go from this more east-west direction to this more north to south direction as shown right here. And the other thing you would look for here is maximum winds developing at lower altitudes as well. Finally, as the flare-up is dissipating, the flare-up poleward boundary becomes more east-west oriented, and I'll show that right here. Also, cloud tops warm, and the cloud pattern becomes more irregular and accelerates eastward. That's the whole sequence. I'll go ahead and run through this again here. And remember, the key signature in summary here is a trough that's amplifying, moving toward the south. We see a flare-up in the mid and high-level clouds, and then they become more oriented from more east to west to more north to south, or more meridional. And then as it's dissipating here, it goes back to more east to west oriented, and warming cloud top temperatures and the more irregular signature in the water vapor imagery. Here's the TPW loop highlighting the ITZZ flare-up from the previous loop. Here we applied an enhancement which will focus us on the lower PW values shown in the subtropics. The higher PW values in the tropics are whited out down here. So the signature we're looking for, I'll go ahead and stop it. the signature we're looking for is this plume of moisture right here. And what's happening is out ahead of that trough, you see those clouds develop at mid and high levels, and higher TPW is drawn up and advected in this direction right here. TPW can be used to track ITZZ flare-ups as well, and also give you a better idea in terms of the precipitation, where the higher TPW values, of course, would correspond to higher probability of rain. Here's an example of an ITZZ flare-up in the Atlantic. Note this case occurs during the spring. An ITZZ flare-up develops ahead of a strong tutlow that is approaching tropical latitudes. I'll go ahead and speed up the loop here. So you can see this strong low that's approaching tropical latitudes here. The warm conveyor belt, in this case, develops in northern South America, and you can see it advecting towards the northward here, towards Puerto Rico. Flash flooding was the result of this event. There was quite a bit of flash flooding in Puerto Rico associated with this particular event. Here's the TPW data from a POSE satellite. This data clearly shows a plume of higher TPW that advects from northern South America towards the vicinity of Puerto Rico. The plume of maximum TPW corresponds well with the ITZZ flare-up in the water vapor imagery. The higher TPW signature was key in recognizing a flash flood event. That concludes this training session. Our conclusions here are a review of the topics we have been discussing. First off, we looked at tropical cloud identification. Then we looked at mesoscale vortices, such as MCVs. We looked at differential heating and various effects associated with that, such as island effects and sea breeze. We spent a lot of time on easterly waves, identifying them in the satellite imagery and other types of data. We looked at surge lines, and then finally, we looked at ITZZ flare-ups. Thank you for taking this training session.